Okay, today we study these three topics. In the first topic, I want to compare the three interpolation approaches that I introduced in the last class. The second topic, we studied section 2 in this chapter. Now, topic 1. Suppose we are given a table of some function values about function f. Our goal is to find a polynomial. I call this polynomial P. The degree of P is not greater than n, such that this polynomial interpolates this table. In other words, satisfies this n plus 1 conditions. Such a polynomial is one and only one by theorem. There are three approaches to construct such a polynomial. Take a review. The number one is random interpolation. We express the polynomial P in the powers of x. Degree n. Then taking this n plus 1 conditions, we have a system of linear equations. Substitute the conditions in one, then we get a linear system. 1 x0 squared x0 n and so on. 1 xn squared xn to n. This coefficient matrix with special structure, we call this matrix random matrix. The unknowns are a1, a0, a1, an. Then equal to the right side. Right side is function value. Function values. Random matrix, it is well known, highly ill conditioned. This matrix is very sensitive to round-off error. So if you find interpolation polynomial in this way, the solution is highly inaccurate. Therefore, in practice, this method is not recommended. And also, look at the coefficient matrix. This matrix is a dense matrix. Dense matrix. That means most of the entries are non-zero. Such a matrix, such a linear system, if you solve it, the computational cost, the cost is very high. Cost is n cubed. The number of floating point operations is n cubed, order n cubed. So computational cost also very high. After you solve the linear system with so high computational cost, you get a solution, but the solution highly inaccurate. So in practice, low people use random interpolation to compute interpolation polynomial. This is approach one. Now the second approach. Second approach Lagrangian interpolation. The idea is first construct a polynomial to some special tables of data. X0, X1, xk minus 1, then xk. K is between 0 and n. At sk, function value is 1. At other rows, function values are zeros. The polynomial that interpolates this table can be written down immediately. The polynomial interpolation polynomial to this table is let me use L to denote the polynomial. Lk is x minus x0, x minus x1 times x minus xk minus 1. Yeah, minus is root. And then skip xk times x minus xk plus 1 times x minus xn. If you expand this product, you will see it is a polynomial of degree n. Then divided by function value at xk is 1, so divided by xk minus x0, xk minus x1, xk minus xk minus 1 times xk minus k plus 1. We, according to the book, we call this polynomial a cardinal polynomial. Okay, after we construct polynomials to these special data tables, then it is easy to find the interpolation polynomial to the original table. So the polynomial to the original table is just a function value at x0 times L1, L0 times L0, then plus function value at x1 times L1 plus function value at xn times Ln. In at least one situation, people like to use Lagrangian interpolation. The situation is, okay, one situation people often prefer Lagrangian interpolation. Okay, one situation. The situation is, okay, when people has a single set of fixed sk values. Yeah, the roots are fixed, but the function values are with many different y means a function value, y is f of x, yk values associate with the x values, sk values. Yeah, in this situation, people prefer Lagrangian interpolation. Say, for example, in an experiment, repeat that experiment many times. Okay, so in the case, X values are fixed, but the Y values, many different Y values. So in the case, the cardinal L are the same because the X are fixed. Cardinal are the same, but the Y values are different. So for one set of Y value, one set of experimental data, I construct a polynomial. For the other set of Y values, because the same cardinal functions, so we can immediately write down interpolation polynomial for other different set of Y values. So very, very convenient, this approach. So in this situation, people prefer Lagrangian interpolation. Then how about Newton? Okay, Newton. The third approach that I introduced you in the last class is Newton interpolation. Then what is the advantage of Newton interpolation? Interpolation. This approach is first construct some special polynomials. Say Q0 is one constant polynomial. Q1 is x minus x0. Q2 is x minus x0, then minus 1 times, and so on. Q3 is x minus x0, x minus x1, x minus x2. Okay, don't minus x3. Okay, and so on. First, construct a sequence of special polynomials. Then write the interpolation polynomial that we want to find as a linear combination of these special polynomials. It is C0 times Q0, then plus C1 Q1, C0 C1. These coefficients will be determined. C2 Q2, and so on, and then Cn Qn. Then plug in the interpolation conditions into that polynomial. We get a linear system. Substitute conditions in equation 1. Then we have a linear system. The linear system is 1, 0, 0. 1 Q1 at x1, then 0. The coefficient matrix is a lower triangular matrix. Q1 at x2, Q2 at x2. Then the fourth entry is 0. That's 0, lower triangle, and so on. One Q1 at xn, Q1, Q2, Q2 at xn, and Qn at xn. A lower triangular matrix. And then the unknowns are C0 C1, C2, and Cn. Right hand side is function values. Because the coefficient matrix is lower triangular matrix, the solution of this linear system, the computational cost is not high. Okay, the computational cost is order n squared, not order n cubed. Yeah, n squared acceptable. Okay, acceptable. This cost is not high. Okay. Then what is the advantage of Newton interpolation over Lagrangian interpolation? There is one situation. Yeah. Let me write down the situation. One situation. Okay. A situation. People often use Newton's method rather than Lagrangian. A situation. If more data are added to the interpolation problem, okay, then Newton's method, it turns out that the coefficients C, okay, coefficients that are already computed will not have to be computed again. And let me show you one example. Okay, we have originally we have this table. And we have found, okay, we have found the interpolation polynomial to this table. P, let me call this polynomial Pn. N means the degree n. Okay, we have found the interpolation polynomial to this table Pn. Suppose. Okay, now we want to add, say, one new data point to the table. Okay, now add one more point, add xn plus 1, yn plus 1. This case. To the table, then we get a new table. Yeah, this case, people use Newton's method. Y2, yn plus 1. To this new table, it turns out that the polynomial, let me name the polynomial n plus 1. This is a new polynomial, degree n plus 1. It turns out that it is equals to the old polynomial Pn plus one term. The term is Cn plus 1. Cn will be determined times x minus x0, x minus x1, x minus the last one, xn plus 1. So C0 C1 to Cn, those coefficients have been computed when we construct the polynomial to this table. Those coefficients, you don't need to recompute them. What you need to compute is Cn plus 1. If you add more tables to the original table. So very convenient. Very convenient. Okay. Okay, now the question is, you may ask me, why? This is the interpolation polynomial to this new table. Why? Okay. Let me give a name to the right side. Say Wx. W is a polynomial. Okay. Now, let me prove that W, this polynomial, interpolates the new table. How? Plug in the data points. Plug in 0, then we get Pn x 0, and then Cn plus 1 x 0. Plug in 0 in x minus x 0, x 0 minus x1, x 0 minus xn plus 1. But x 0 minus x 0 is 0, so the second term is 0. It is equals to Pn x 0. But Pn interpolate this table. What it means? Value of Pn at x 0 is y 0. So W at x 0 is value is y 0. Then similarly, plug in x1 in x, then we get also equals to Pn x1, but Pn x1 is y1, and so on. When we plug in xn, we get Pn xn, but Pn xn is yn. So this polynomial interpolates the data points from x0 to xn. Now the last point, okay, plug in the last point. W xm plus 1, okay, then plug in Pn xm plus 1, then Cn xm plus 1 minus x0, right? Xn plus 1 minus x0, then times xn plus 1 minus xn, and so on. Times here. Now, here is not n plus 1, just n. Then times n plus 1 minus xn. We assume the logs are different, so the second term non-zero. Now this should be equal to yn plus 1 because W interpolate the new table, so yn plus 1. Now from this equation, we can determine Cn. So Cn plus 1 is equal to yn plus 1 minus Pn xn plus 1. Yeah, move this to the right side and then divided by this factor. Then we can get Cn plus 1. So in this approach, we only need to compute Cn plus 1. We don't need to compute C0 to Cn. Convenient, save a lot of work. This is xn plus 1 minus 0, and so on. Xn plus 1 minus xn. Yeah. So compute Cn plus 1 by this quotient. That's it. Okay. So in this special situation, people prefer Newton's method. But why people don't prefer Lagrangian interpolation in this case? When we have some new data points add to the original table. Then we need to reconstruct the cardinal function. We need to construct, right? Ln plus 1. Yeah. Yeah. The cardinal function associated with the new table are very different from the cardinal functions associated with the old table. So in this situation, Newton's method. In the previous situation, yeah. In this situation, people prefer Lagrangian interpolation when one experiment is repeated again and again. Lagrangian interpolation. So this is a comparison among these three approaches. Random interpolation is always not recommended. This is a topic one. Second topic. Section 2. Divided differences. Topic 2. Again, we are given a table of function values. Function values. Yeah, this time let me use function value at x0, function value at x1. As we have seen, three approaches to find interpolation polynomial. In this section, in section 6.2, we focus on Newton's interpolation. Newton's interpolation. Because Newton's interpolation is relatively easy to be extended to more complicated problems. Lagrangian interpolation, not easy to be extended to other problems. So let's focus on Newton's interpolation. Okay. In Newton's interpolation, we need to solve a lower triangular linear system. Okay. In Newton's method, Newton's interpolation. Okay. We need to solve a lower triangular linear system. Let me repeat this linear system. Zero. 2, 1. Yeah, Q1 at x2. Q2 at x2. Then Q2 at x3. That is 0. Q1 at xn. Q2 at xn. Qn at Q3 at xn, and so on. Qn at xn. Then the coefficients are C0, C1, C2, and Cn. Right side is function values. Function values. Yeah. Where the coefficients are the polynomial, interpolation polynomial of this form. This is C0 times Q0 plus C1 times Q1, and so on, plus Cn times Qn. Right. When we solve this linear system, we can see that, say from the first row times the unknown vector equals to the right side, then we can see that Cn C0 is just function value at x0. When we solve the second equation, second row times the vector equals to the second entry on the right side, then we will see that C0 plus C1 Q1 x1 is equal to function value at x1. Okay, C0 we got it function value at x0, and then plus C1. Q1, recall that Q1, this polynomial is x minus x0. So this is a x1 minus x0 is function value at x1. Okay, then we get C1 is f x1 minus f x0, then over x1. Yeah. So from C0 and C1, we see that C0 only depends on function value at x0, and C1 only depends on function value at x0 and function value at x1. Similarly, if you solve the third equation, the third row times the unknown vector equals to the third entry, you will see that C2 only depends on let me separate. Only depends on function value at x0, function value at x1, function value at x2. In general, CK only depends on function value at x0, at x1, and at xk, at sk, at sk. And now to emphasize this dependence, we use the following notation. Okay, we below CK. CK is the coefficients in the Newton interpolation polynomial. We use this notation. Function. Okay. Here. Square brackets. Not use parentheses. X0, x1, xk. Yeah. In this way, we emphasize that the coefficients in Newton's polynomial CK only depends on function values at x0, x1 to xk, not on xk plus 1, not on xk plus 2 and xn. Okay, yeah, this rotation. Okay, now let's give a name to this rotation. Let me call it. Okay, we call it divided difference of how many points? K plus 1 points. So here, all the K of function f. Some of you may ask me why we don't use CK for the coefficients of the Newton interpolation polynomial. Why we use this notation? Because this notation is helpful in later developments, is helpful in the solution of more complicated problems. Okay. Now, from now on, we don't use CK for the coefficients of Newton's interpolation polynomial, but use this notation and give a name. Divided difference of order K of function f. Okay, now you may ask me the question, why name this guy divided difference? Yeah, from here. C0 is function value. Yes. Yeah. Okay. F x0. This is a divided difference of order 0. It is. Yeah. This is it is C0. C0 is function value at x0. Yeah. Here from here. I solved this linear system to get this. Then from the second equation of the linear system, I got this. I got this. Therefore, divided difference of order 1. Actually, this is just coefficient C1. It is equals to what here? Yeah. Here. Function value at x1 minus function value at x0, then over x1 minus x0. Yeah. This is a divided difference. Say difference divided. So that's why we give a name to see to this guy. Divided difference. Yeah. This is a hint for this name. Okay, for this name. Okay, so divided difference is nothing new, just the coefficients of Newton interpolation polynomials. Okay. All right, let me put a remark. If we expand, okay, the Newton polynomial, Newton polynomial is here. Okay, this is a C0 plus C1, then times Q1. Q1 is x minus x0. Then C2, x minus x0, x minus x1. Then plus Cn, x minus x0, x minus x1, x minus xn minus 1, not xn. Okay. If we expand this polynomial into a polynomial in the powers of x, say let me A0, A1, x, A2, x squared, and then an, xn. Then we see that an, the leading coefficient, is equal to Cn. Yeah, compare. Okay. This polynomial, the leading coefficient is Cn. This polynomial, the leading coefficient is An. Actually, they are equal. Okay. In the divided difference notation, actually is this. Xn. Okay. Then for the leading coefficients, compare the leading coefficient, we have this equation. But for other coefficients, we don't have this equation. Okay, usually we don't have. Okay, A, K usually don't equal to CK. Okay, don't equal to CK. Yeah. In the divided difference notation, this is K usually. Okay. Yeah. Pay attention about this remark. At some later point, we use this result. The leading coefficients are equal. Okay. This is topic 2. I introduce you what is divided difference. Nothing new, just the coefficients of Newton polynomial. Now topic 3. Higher order divided differences. Order 0, order 1, low order divided difference. Higher order, say when K is large, order K large, higher order. Then we want to develop a formula to compute higher order divided differences. Okay. Of course, you can compute higher order. You can compute divided difference by solving this equation, because divided difference are just coefficients. But this approach, solve this linear system, is a sequential approach. What it means? To get x1, you first compute x0, c0. To get c2, you need to first compute c0 and c1, then get c2. This is a sequential approach. Now, in the following, we present approach to compute the coefficients parallelly. Okay, yeah, that new approach can be implemented in parallel. Okay. Okay, now let me present a formula to compute higher order divided differences. This is topic 3. Topic number 3. It is a theorem in the book. Okay, consider this table. Xn. Function value at x0, function value at x1, function value at x2, xn. All right, now we define divided difference at x0. Yeah, this is an order 0. Is equal to just the function value at x0. Similarly, divided difference at x1, the order of this difference is still order 0. Function value at x1. And similarly, divided difference at x2 is function value order 0. And so on. And so on. Okay. Then we have the following formula. Divided difference of order k is equal to divided difference of order k minus 1 and the points x1, x2. Okay, starting from x1, not starting from x0. Xk. Then minus, this is a order k minus 1 because k points. Here, k plus 1 points. This difference is called order k. K points, order k minus 1. Then minus, now this time, start from x0, x1, then xk minus 1, then over xk minus x0, xk minus 0. Okay, now the proof actually the proof is easy. Okay, without loss of generality. Okay, without loss of generality, we can assume k is n because the data points x0, x1, x2, xn. Actually, you can build them, arbitrary data points in this field. Okay. Without loss of generality, we assume this k is n. Okay. Now, then Pn, the interpolation polynomial. Interpolation polynomial of function f and Pn here degree is n at x0, x1, xn. Then Pn minus 1 be the interpolation polynomial of the function at x0, x1, then xn minus 1. Okay, and Q the interpolation polynomial of the function at x1, x2, and xn. Okay, then it's easy to verify that Pn, this polynomial, is equal to Q n minus 1. Actually, yeah, let me n minus 1. Yeah, the polynomial interpolate these n points. Degree is n minus 1. Then plus xn. Qn minus 1. X. Left side is polynomial, right side polynomial, and also both polynomials degree n. Left side interpolate x0, x1, xn. Yeah. The right side also interpolate x0, x1, xn. How to see that? Plug in x0 in x, then you will see that the right side is equal to f of x0. Plug in x1 in the x on the right side, then the value is this, and so on. So left side, right side interpolate the same table by the uniqueness of interpolation polynomial. Left side is equal to right side. Now compare the leading coefficients. Left side, the leading coefficient is Cn. Cn is this by notation. Okay. The right side leading coefficient is this guy degree is n minus 1. So the leading term just x to n minus 1. We are looking for the coefficients of the term x to n. So this guy contribute nothing to the leading term. So the leading term is from here. The leading term is this. x1, x2, xn. Yeah, this is the leading coefficients of this polynomial. Minus leading coefficients of this polynomial is this. Then over this xn over this number. This is a constant. And this equation is this equation. So the proof is done. The proof is done. Okay, now in the next class, I will use this formula to compute the coefficients of Newton interpolation polynomials. This approach by this formula can be implemented in parallel. Okay, solving linear system, lower triangular linear system, the approach can only be implemented sequentially. Okay, sequentially. Okay. Okay, let me make a summary about today's class. Okay, this guy, nothing new, just the coefficient ck in the Newton polynomial. Why we introduce a new notation? Because it turns out that this new notation is helpful in developing methods to solve more complicated problems. Okay, that is later stories. Yeah, let me stop today's class here.